Hello, I'd like to do a quick lesson on determining sample size, and I'll do an example from the textbook as well. But first, let's start with our basic formula for confidence intervals. So the confidence interval formula is x bar plus or minus the critical z-score, like 1.96 or 95%, etc., whatever it happens to be, times the standard deviation of the sampling distribution, which is sigma over square root of n. Now, this part of the formula is called the margin of error, right there. After you do that calculation, you'll know your margin of error. All right, so suppose that you're going to do some research and you have particular requirements you must satisfy. For example, let's say you have a desired margin of error, you have a known population standard deviation, and you have a desired confidence interval that gives you a z, it gives you a sigma, it gives you the margin of error. But the question we want to find out here is how big does the sample have to be? Does the sample have to be? And in general, you're solving for n. You're taking this formula right here, and you know all the information you need except for n. So in other words, solve for n. Oops. Solve. That's an L right there. It's a badly written L. Solve for n. Okay, let's take a look at an example. This is chapter 15. No, excuse me. This is chapter 16, question 42. Here it is. It says, "This wine stinks." It says, "How sensitive are the untrained noses of students?" So we did this question earlier, but now we're looking at it in the context of what the sample size should be. So exercise 14.27 gives the lowest levels of DMS, dimethyl sulfide, I believe is how you say it, that 10 students could detect. You want to estimate the mean DMS odor threshold among all students, and you would be satisfied to estimate the mean to within plus or minus 0.1, and that would be, doesn't give the units there, 0.1, what was it, micrograms per liter, I think it was, with 99% confidence. The standard deviation of the odor threshold for untrained noses is known to be sigma equals 7 micrograms per liter of wine. How large does a simple random sample of untrained students do you need? Okay, let's go back to our whiteboard here. So n, we don't know. That's what we're looking for. So in the question, it asks us to get a 99% confidence level. Okay, so that means z, the z star, the critical z, must be 2.576. That's just the standard z score for 99% confidence. Also in the problem, they tell us that sigma is equal to 7 micrograms per liter. And they have a desired margin of error. Let's use m for margin of error. Some people use e for error. That's fine. I'll just use m here. M is equal to 0.1 micrograms per liter. Okay, so back to our formula here. I'm going to take this part of the formula and set that equal to m. So I'm going to have m, margin of error, is equal to that critical z-score times sigma over square root of n. Okay, so we know m, we know z, we know sigma. Just algebraically solve for n. So there's two ways to do this. One way to do this is just plug in all your numbers and then solve for n. So you would go 0.1, replace the n with 0.1, z star 2.576 times sigma, which is 7, divided by square root of n. Okay, so just solve for n there. That's method 1. Well, let's go ahead and do this first. So 2.576 times 7. You could think of this as 2.576. over 1. I'm multiplying two fractions together. So let's get out a calculator here. Let's go to our standard calculator. So 2.576 times 7 is 18.032. So I've got 0.1 equals 18 point, what was it again? 18.032 divided by square root of n. Okay, multiply both sides by square root of n, divide by 0.1, so I get square root of n equals 18.032 divided by 0.1, and then divide 18.032 divided by 0.1, and that gives us 180.32. Dividing by 0.1 the same as multiplying by 10, so I'll just move this point over a place. If you don't trust me on that, you can just take 18.032, divide by 0.1, and sure enough, 180.32. Now, to solve for n, I have to square both sides. So I'm going to square this side, and that's going to give me a pretty big number there. 180.32 times 180.32 is 32,515.3. So that's a huge sample size, but then that's because we have terribly strict criteria here. We need a super small margin of error, only 0.1 micrograms per liter, and we have a really high confidence. So the only way we can satisfy both of those conditions is to have a really big sample. All right, now of course sample size is the number of individuals. You can't have 0.3 of an individual, so in general you round up. 32,515 is not quite enough, so let's round it up to 3,516. Okay, there's the answer, and that would be people, or untrained students would be the actual type of people that we need for this study. Okay, so the question you need to ask yourself is it worth it? Because you got to pay a lot of money to get a sample that size. Is it worth it to get that many people in a sample just to get that margin of error to be that small? Well, maybe it is, maybe it's not, but that's another issue altogether. But anyway, that's the answer to the question. Now, let me show you method 2. So same problem, but the idea here is instead of solving for n algebraically like I did here, I like this method myself because it's one less thing to remember. It's just the same old margin of error formula that you use with your regular constant interval problems. But if you want to, you can algebraically rearrange this formula for n. And in the textbook, they do that for you. Let me do this real quick here for you. So m equals critical z times sigma over square root of n. So method 2 is you algebraically rearrange your formula for n first. So move the n up. I have square root of n. Move the m down. I'm going to have z star sigma over m. And then square both sides. And I get n equals z star times sigma over m all squared. Okay, then once you have your formula, then you can go ahead and just plug in your numbers. Plug in this case, 2.576 for z star, 7 for sigma, 0.1 for m. Do the arithmetic, and you'll get the same answer either way you do it. And this formula is given to you in the textbook towards the end of chapter 16 on page 401 of the textbook. That's it.